The finest torpedo of World War II killed more Allied cruisers and destroyers than any other single weapon in the Pacific, yet the United States Navy spent 2 years believing submarines were responsible. Before we go deeper into how this decision changed the Pacific War forever, make sure to subscribe for more history that actually happened. On the night of August 9, 1942, 3 American heavy cruisers, Quincy, Vincennes, and Astoria, burned against the Black Water off Savo Island. The Australian cruiser Canberra lay dead in the water, her captain killed, her hull ripped open. More than 1,000 sailors died that night in 37 minutes of violence so swift that most never understood what hit them. American commanders, scrambling for explanations, concluded that Japanese submarines must have infiltrated the channel. The alternative seemed impossible. No surface-launched torpedo could strike from such distances. No warhead could punch through 8 inches of armor plate with such devastating effect. No weapon could travel 15 miles at 48 knots and arrive precisely on target. But all 3 cruisers had been destroyed by torpedoes fired from surface ships. The Japanese had achieved what every other navy in the world considered fantasy. They had built a torpedo that used pure oxygen as its oxidizer, creating a weapon so advanced that Allied intelligence would not fully comprehend it until captured examples were examined in 1943. The Type 93 torpedo, later nicknamed the Long Lance by American naval historian Samuel Eliot Morison, represented the culmination of 15 years of dangerous experimentation, countless explosions, and the willingness to weaponize one of chemistry's most volatile substances. In 1922, the Washington Naval Treaty forced Japan into an uncomfortable position. The agreement limited capital ship tonnage to a 5-to-5-to-3 ratio, 5 for Britain, 5 for the United States, 3 for Japan. Japanese naval planners understood the mathematics of defeat. If war came with America, the Imperial Japanese Navy would face an opponent with 60% more battleships. American doctrine, codified in War Plan Orange, anticipated exactly this scenario. The Pacific Fleet would steam westward from Pearl Harbor, relieve the Philippines, and destroy the Japanese fleet in one climactic engagement somewhere in the western Pacific. This was Mahanian naval theory in its purest form, the decisive battle that would determine control of the ocean. Japan could not win such a battle. Not fairly. So Japanese strategists developed a different approach, one that would transform tactical disadvantage into strategic opportunity. They would whittle down the American fleet before the decisive battle ever occurred. Light forces, cruisers, destroyers, submarines, would harass the advancing American armada in a series of attritional engagements, each one reducing enemy strength by a few percentage points. By the time the surviving American battleships reached Japanese waters, they would face a numerically equal opponent. The climactic battle would be fought on even terms. But this strategy required a weapon that could allow small warships to cripple large ones. It required a torpedo unlike any that existed in 1922. It required engineers willing to experiment with substances that other navies had abandoned as too dangerous for operational use. Rear Admiral Kaniji Kishimoto took command of the torpedo development program at Kure Naval Arsenal in 1928. He inherited a problem that had stymied weapons designers across the world: compressed air. Every torpedo of that era used compressed air to oxidize its fuel, whether alcohol, kerosene, or gasoline. The torpedo's engine worked like any internal combustion system: fuel mixed with oxygen, ignited, expanded, and drove pistons that turned propellers. But air is 78% nitrogen, an inert gas that contributes nothing to combustion. It simply takes up space in the torpedo's pressure tanks. Nitrogen also creates the torpedo's most visible flaw, the wake. As the engine exhausts hot gases through the torpedo's tail, nitrogen bubbles rise to the surface, marking the weapon's path with a white trail that alerts the target and reveals the firing ship's position. If a torpedo could eliminate nitrogen entirely and use pure oxygen instead, the advantages would be dramatic. With nearly 5 times more oxidizer in the same volume, range would increase exponentially. Speed could be pushed higher. The warhead could be larger. And the wake would virtually disappear. Carbon dioxide dissolves rapidly in seawater, and water vapor leaves no bubble trail. The idea had occurred to other nations. The British Navy had experimented with oxygen-enriched torpedoes for the Nelson-class battleships, though these used oxygen-enriched air rather than pure oxygen. A Japanese naval officer stationed in Britain during the 1920s observed these trials and brought the concept back to Japan with a crucial misunderstanding. He believed the British were using pure oxygen. This error would prove productive. Japanese engineers at Kure, attempting to replicate technology that did not quite exist, would surpass it. But first they had to survive the development process. Pure oxygen does not simply burn. Under pressure, it explodes. Introduce any combustible material, a trace of oil, a particle of dust, a moment of friction, and the result is catastrophic detonation. American and European torpedo designers had conducted preliminary tests with oxygen systems in the early 1920s. All had concluded that the risk was unacceptable. A single malfunction could destroy the torpedo, the launcher, the handling crew, and potentially the ship itself. Japan's weapons engineers reached a different conclusion. They decided the risk was acceptable. Between 1928 and 1933, the Kure facility experienced more than 200 explosions during oxygen torpedo testing. Engineers died. Equipment was destroyed. Entire workshops were rebuilt. But with each failure, the team learned. They discovered that starting the engine with compressed air and gradually transitioning to pure oxygen prevented the initial detonation that had plagued earlier attempts. They developed special alloys for the oxygen tanks that resisted oxidation. They created elaborate safety protocols for handling, loading, and firing the weapons. To maintain secrecy, and to keep nervous ship crews from understanding what they were working with, the pure oxygen tank was labeled the secondary air tank. Only trained specialists knew what it really contained. By 1932, Captain Toshide Asakuma had refined the engine design to the point where it could sustain combustion with pure oxygen without exploding. The torpedo measured 29 feet 6 inches long with a diameter of 24 inches, substantially larger than any torpedo then in service. It weighed 5,952 pounds, nearly 3 tons of steel, oxidizer, fuel, gyroscope, and warhead. The gyroscope was a precision instrument spinning at thousands of revolutions per minute, maintaining the torpedo's course even across ranges that would take 15 minutes to traverse. The warhead contained 1,080 pounds of Type 97 explosive, a Shimose-type compound approximately 7% more powerful than TNT. This was more than double the explosive charge carried by American torpedoes. The specifications that emerged from testing seemed almost fictional. At 48 to 50 knots, the Type 93 could travel 24,000 yards, more than 13 nautical miles. At 36 knots, range extended to 44,000 yards, or 25 miles. Even at this lower speed setting, it outpaced the American Mark 15 torpedo at maximum velocity. The Mark 15, standard equipment on every U.S. destroyer, could reach 15,000 yards at 26 knots or 6,000 yards at 45 knots, carrying an 827-pound warhead. The Japanese weapon outranged its American counterpart by 3 to 1 at comparable speeds. In practical terms, this meant Japanese destroyers could launch torpedoes from distances where American ships believed they were safe from torpedo attack. The psychological impact would prove as devastating as the physical destruction. The Imperial Japanese Navy deployed the Type 93 operationally in 1935, equipping the newest classes of destroyers and virtually every cruiser in the fleet. Installation required more than simply mounting launcher tubes on deck. Each ship needed an oxygen generation system, a complex apparatus that used electrolysis to separate oxygen from water, then compressed and stored the gas in reinforced tanks. These systems were temperamental, requiring constant maintenance and careful operation. A leak could create an oxygen-rich atmosphere that would turn any spark into an inferno. Engineers developed elaborate safety procedures. Before a torpedo could be loaded into its tube, compressed air had to be bled through the system to purge any residual oxygen. The torpedo itself was loaded with its main oxygen tank pressurized to 550 pounds per square inch, more than 30 times atmospheric pressure. A starting air flask, much smaller, contained regular compressed air at even higher pressure. When the torpedo launched, this compressed air mixed with kerosene fuel and ignited in a heat starter. The engine began running on this safe, conventional fuel mixture. Then, as the compressed air depleted and pressure dropped, a regulator valve opened and pure oxygen from the main tank flowed into what was now the compressed air reservoir. Within seconds, the entire system ran on oxygen and kerosene, a combination powerful enough to drive the torpedo at speeds no other navy could match. Japanese destroyer and cruiser crews practiced endlessly with these weapons. The Imperial Navy had committed to night combat as its primary tactical doctrine, and night combat meant torpedo engagements at ranges where gun accuracy deteriorated. Crews trained to launch spread salvos, multiple torpedoes fired at staggered angles to bracket a target's predicted position. They practiced reload drills, training to launch a second salvo within minutes of the first. Some Japanese destroyers mounted their torpedo tubes in armored turrets with ready-use reloads immediately adjacent, allowing sustained fire during extended engagements. The most capable destroyer classes carried 16 tubes with 8 reloads, giving them the ability to fire 24 long-lance torpedoes in a single action. For comparison, American destroyers typically carried 10 torpedo tubes with no reloads. This disparity in magazine depth would prove decisive in several engagements. The first large-scale test of the Type 93 came in darkness, as Japanese doctrine intended. On February 27, 1942, Admiral Karl Dorman led a combined American-British-Dutch-Australian force against the Japanese invasion fleet approaching Java. 5 cruisers and 9 destroyers steamed to intercept. The Japanese force numbered 4 cruisers and 13 destroyers, including the heavy cruisers Nochi and Haguro, both equipped with 16 Type 93 torpedo tubes. The battle began in late afternoon with long-range gun exchanges that accomplished little. Neither side scored significant hits. As twilight descended, the Japanese withdrew temporarily, luring Dorman's force deeper into waters favorable to torpedo attack. At 1,633 hours, the light cruiser Naka launched for long-lance torpedoes from 15,000 yards, more than 8 nautical miles. These missed. The Allied commanders barely noticed. Torpedo attacks at such distances were considered impossible. Western naval doctrine held that torpedoes fired beyond 10,000 yards were wasted, they would either run out of fuel or their target would have time to maneuver clear. At 1,708 hours, with range close to 22,000 yards, Haguro launched a spread of torpedoes. One of these struck the Dutch destroyer Kortenaar. The ship simply vanished. A massive explosion tore her in half, and both sections sank within minutes. This was not the normal appearance of a torpedo hit. The detonation was too violent, too complete. Allied officers concluded Kortenaar had struck a mine. The idea that a torpedo could hit from that distance, from beyond the horizon in terms of visual range, did not occur to them. The battle continued into darkness. Japanese cruisers and destroyers maneuvered freely, their crews trained for night combat and equipped with excellent optical sights. At 2,306 hours, Nochi and Haguro launched another spread of long lances. These torpedoes ran through black water for more than 10 minutes. The Dutch light cruiser Java, attempting to evade gunfire, maneuvered directly into the torpedo's path. One struck her amidships. The explosion was catastrophic. Java's magazine detonated, and the ship disintegrated, taking most of her crew down instantly. Moments later, another torpedo slammed into the Dutch flagship De Ruyter. The heavy cruiser's back broke. She capsized within 30 minutes, taking Admiral Dorman with her. The Battle of the Java Sea represented the longest-range torpedo hits in naval history. Haguro's torpedoes covered more than 11 nautical miles before striking Kortenaar. Yet Allied survivors remained convinced that submarines were responsible. The official reports attributed multiple sinkings to submarine action in concert with surface forces. This misunderstanding would persist for more than a year, allowing Japanese destroyers and cruisers to maintain a critical advantage in subsequent engagements. At Savo Island for months later, the pattern repeated with even more devastating results. On the night of August 8 to 9, 1942, Vice Admiral Gunichi Mikawa led 7 cruisers and 1 destroyer through the channel between Guadalcanal and Savo Island. His objective was to attack the American transport ships unloading supplies for the Marine invasion force. To reach the transports, he had to pass through a screen of Allied cruisers. American and Australian forces had positioned themselves to intercept any Japanese approach, 3 heavy cruisers patrolling south of Savo Island, 2 heavy cruisers and a light cruiser to the north. Mikawa's force approached from the northwest at 26 knots, maintaining strict radio silence. At 0136 hours, Japanese lookouts spotted the destroyer USS Blue on radar picket duty. Blue failed to detect the Japanese column. At 0143 hours, Mikawa's ships launched reconnaissance floatplanes. These aircraft circled the area, their engine noise masked by a passing rainstorm. The pilots radioed back precise positions of every Allied ship. At 0145 hours, the heavy cruiser Chokai illuminated the destroyer USS Jarvis with searchlights and opened fire. The night action at Savo Island lasted 37 minutes. In that time, Japanese cruisers and destroyers fired 93 torpedoes, the vast majority were Type 93s. They fired from ranges between 8,000 and 12,000 yards, distances American commanders considered beyond torpedo threat. The northern group of Allied cruisers, Vincennes, Quincy, and Astoria, found themselves caught in a crossfire. Japanese ships approached from both flanks, launching torpedoes and following up with gunfire. Quincy took a long lance hit on her port side that flooded 2 fire rooms and destroyed steering control. Additional torpedoes struck as she tried to maneuver. She sank at 0238 hours. Vincennes absorbed multiple torpedo hits. The 1,080-pound warheads punched through her armor belt, detonating inside the hull and rupturing fuel tanks and magazines. She capsized and sank at 0250 hours. Astoria, hit by torpedoes and gunfire, burned out of control until she was scuttled the following morning. The Australian cruiser Canberra, in the southern group, took 2 torpedo hits and 24 shell impacts. Her captain was killed, her engineering spaces flooded, her guns silenced. The Allies scuttled her the next day. Only 1 Japanese ship suffered significant damage. Chokai took 3 8-inch shell hits. None of Mikawa's cruisers or destroyers were sunk. The battle represented the worst defeat of the U.S. Navy in a fair fight, for heavy cruisers lost in exchange for minor damage to 1 enemy cruiser. Yet in their action reports, American survivors consistently attributed torpedo hits to submarines. The official record stated that torpedoes fired from submarines in concert with surface forces sank multiple cruisers. Sonar operators reported hearing submarines maneuvering nearby. Lookouts claimed to spot periscopes. In reality, every torpedo strike came from surface ships firing Type 93s from what American doctrine considered impossible ranges. The psychological shock of this defeat resonated through the Pacific Fleet. Cruiser captains became reluctant to close with Japanese forces at night. Destroyer commanders hesitated to press home attacks. The U.S. Navy, which had trained for daylight gun actions, struggled to adapt to an enemy that owned the darkness. The weapon's true capability became undeniable on November 30, 1942, off Tassafaronga Point on Guadalcanal's north coast. Rear Admiral Reizo Tanaka commanded 8 destroyers on a supply run, the Tokyo Express fast transport missions that had kept Japanese forces on Guadalcanal fed and armed throughout the campaign. American forces had learned to expect these runs. Rear Admiral Carlton Wright positioned 4 heavy cruisers and a light cruiser, screened by 6 destroyers, to intercept. Wright's force possessed overwhelming firepower, 37 8-inch guns, 28 5-inch guns, radar fire control, and numerical superiority. At 2,306 hours, radar aboard USS Minneapolis detected Tanaka's column at 23,000 yards. Wright's ships closed to 7,000 yards before opening fire. The American destroyers launched 20 torpedoes. All missed. The cruiser's 6 and 8-inch guns pounded the lead Japanese destroyer Takanami, setting her ablaze. She would sink within the hour. American gunfire control was superb. Searchlights illuminated targets. Radar tracked ranges. Wright's flagship New Orleans was preparing to cease fire when, at 2,320 hours, Japanese torpedoes arrived. The destroyers in Tanaka's column had reversed course and fired 44 Type 93s during the gun action. These torpedoes traveled through the water at 48 knots for nearly 8 minutes before reaching the American cruiser line. Minneapolis took 2 hits on her port bow. The first explosion tore away her entire bow section forward of turret 1, 125 feet of the ship simply ceased to exist. The cruiser's forward momentum drove seawater back into the hull, flooding compartments and drowning men trapped below. Only emergency damage control saved her from sinking. New Orleans, following close behind, took a torpedo hit that detonated her forward magazines. The bow, including turret 1 and turret 2, broke off and sank immediately. The main hull wallowed in the water, her forward bulkheads barely holding. Pensacola took 1 torpedo that punched through her armor belt and exploded in her engineering spaces, killing 125 men and knocking out 3 of her 4 fire rooms. Northampton absorbed 2 hits amidships. Her crew fought flooding for 3 hours before she capsized and sank at 0304 hours. Only Honolulu escaped damage, having maneuvered violently when her captain spotted torpedo wakes approaching. Tanaka's destroyers retired at high speed, having traded Takanami for 4 American heavy cruisers, 1 sunk, 3 crippled so badly they would be out of action for more than a year. The Battle of Tassafaronga crystallized the Long Lance problem. American commanders could no longer attribute the damage to submarines. The engagement occurred in restricted waters where submarine operations would have been suicidal. Tanaka's destroyers had been under continuous observation and gunfire. Yet they had inflicted catastrophic damage despite being outgunned and outnumbered. The only explanation was that Japanese torpedoes possessed capabilities far beyond what American naval intelligence had estimated. Post-battle analysis began to reveal the truth. Survivors reported that torpedoes seemed to come from impossible ranges. They described larger explosions than American torpedoes produced. They noted the near absence of bubble wakes. Japanese torpedoes left minimal surface trails. When intelligence officers finally obtained intact Type 93 specimens in mid-1943, the specifications shocked them. American torpedo designers had believed that 40-knot speeds and 20,000-yard ranges represented the theoretical maximum for torpedo performance. The Japanese had exceeded these limitations by 50%. The discovery forced a fundamental reassessment of Pacific War naval tactics. Behind the Long Lancer's tactical success lay an operational cost that Japanese commanders accepted but American forces exploited. The Type 93's warhead used Shimo's explosive, a picric acid compound more sensitive to shock than TNT. If a ship carrying Type 93 suffered bomb or shell hits near the torpedo storage areas, the warheads could detonate sympathetically. This vulnerability became apparent during the Battle of Santa Cruz in October 1942. The heavy cruiser Chikuma, under air attack from USS Enterprise dive bombers, jettisoned her Type 93 torpedoes just before multiple bombs struck. The torpedoes exploded in the water alongside the ship, causing additional damage but preventing a catastrophic internal detonation that would have sunk her. Other ships were less fortunate. During the Battle off Samar in October 1944, the heavy cruiser Suzuya took a near miss from a bomb that detonated close enough to trigger the Type 93s in her starboard torpedo mounts. The resulting explosions propagated through the ship, setting off additional torpedoes and eventually reaching the main magazines. Suzuya broke apart and sank with heavy loss of life. Japanese cruiser and destroyer captains learned to jettison torpedoes when coming under air attack, but this meant approaching battle with reduced armament or exposing their ships to greater danger if caught by surprise. American carrier pilots noted this Japanese tendency to jettison torpedoes during air strikes. Attack patterns were adjusted to approach torpedo storage areas first, forcing Japanese captains into a terrible choice: accept the risk of sympathetic detonation or reduce their offensive capability. The Long Lancer's effectiveness also declined as the war progressed and American radar technology matured. Early in the war, Japanese destroyers could approach within Long Lance range under cover of darkness, fire their spreads, and retire before being detected. By 1943, American ships routinely detected Japanese forces at 20 to 30,000 yards, well beyond torpedo range. Gunfire could be directed by radar, negating the Japanese advantage in optical fire control. American doctrine shifted toward preventing Japanese ships from reaching torpedo range rather than trying to evade torpedoes after they were launched. Destroyer tactics evolved to emphasize radar-guided night engagements at extended ranges where Japanese night fighting skills could not compensate for American technological superiority. The Battle of Vella Gulf in August 1943 demonstrated the new American approach. Commander Frederick Moosbrugger led 6 destroyers in a night interception of 4 Japanese destroyers attempting another Tokyo Express run. Using radar plotting, Moosbrugger's force positioned itself perpendicular to the Japanese approach and launched coordinated torpedo attacks before the Japanese detected them. American Mark 15 torpedoes, inferior in performance to the Type 93, nevertheless sank 3 Japanese destroyers because they were launched from optimal range and bearing while the targets maneuvered unsuspectingly. The 4th Japanese destroyer escaped but did not fire its torpedoes. The engagement lasted 23 minutes. American forces suffered no damage. This pattern repeated at the Battle of Vella Lavella in October 1943 and the Battle of Empress Augusta Bay in November 1943. American ships used radar to dictate engagement conditions, forcing Japanese forces to fight at disadvantageous ranges where the Long Lancer's superior performance could not compensate for tactical surprise. Yet even in defeat, the Type 93 remained dangerous. At the Battle of Surigao Strait in October 1944, the last battleship engagement in naval history, Japanese destroyers launched Long Lance torpedoes at the American battle line despite being under devastating gunfire from multiple battleships and cruisers. Some of these torpedoes, fired from dying ships, continued toward their targets and forced American battleships to maneuver defensively even as Japanese forces were being annihilated. The destroyer Shiga, sole survivor of the Japanese Southern Force, fired her entire complement of 8 Type 93s while retiring at high speed through narrow waters under continuous fire. None hit, but they forced American cruisers to turn away from pursuit, allowing Shiga to escape. By late 1944, the Imperial Japanese Navy faced a different crisis that compromised the Type 93's effectiveness even more than American countermeasures. Oxygen production facilities required intact industrial infrastructure and reliable electricity supplies. American bombing campaigns disrupted both. The Kure Arsenal, which manufactured most Type 93 torpedoes and oxygen generation equipment, suffered repeated air raids. Submarine warfare interdicted the shipment of torpedoes and replacement oxygen equipment to forward bases. Japanese warships found themselves unable to replenish expended torpedoes or repair damaged oxygen generation systems. Some destroyers entered combat with fewer than half their normal torpedo loadout because oxygen tanks could not be filled. Others carried full complements of torpedoes but were forced to fire them at reduced range settings to conserve limited oxygen supplies. By the time of the Battle of Leyte Gulf, many Japanese destroyers carried Type 93s that had been aboard for months, their oxygen tanks slowly leaking pressure, their gyroscopes uncalibrated because maintenance facilities no longer existed. These torpedoes, once the terror of the Pacific, became progressively less reliable. Many failed to detonate. Others ran erratically, their gyroscopes no longer able to compensate for manufacturing variations or damage sustained during storage. Some exploded prematurely as their aging Shimose warheads became increasingly unstable. The weapon that had sunk 22 Allied warships in the first 2 years of the war claimed only 3 more in the final 18 months, and 2 of those sinkings involved ships that had been crippled by other weapons first. When Japan surrendered in August 1945, Allied technical intelligence teams swarmed over captured naval facilities. At Kure, Yokosuka, and Sasebo, teams of engineers examined oxygen torpedo production equipment, studied maintenance manuals, and interviewed Japanese ordnance officers. What they discovered confirmed the Type 93 sophistication. The weapon's success had required not just advanced design but an entire industrial support system built around handling compressed oxygen safely. Allied nations had possessed the theoretical knowledge to build oxygen torpedoes since the 1920s. What they had lacked was the institutional commitment to accept the development risk. Between 1928 and 1933, Kure Arsenal experienced more than 200 explosions during Type 93 development. Engineers died. Test facilities were destroyed and rebuilt. Ships conducting trials suffered damage. American and British weapons programs would have been cancelled after the first dozen casualties. Japanese engineers continued. This was not simply cultural difference or disregard for human life, it was calculated military necessity. Japan's naval planners understood that their strategic position demanded weapons superior to those of potential enemies. Conventional torpedoes would produce conventional results, and in a conventional naval war Japan would lose. The Long Lance represented an asymmetric capability, a weapon that allowed inferior forces to inflict superior losses. The American post-war torpedo development program incorporated several Type 93 design elements, particularly the concept of extended range at high speed. But American designers never adopted pure oxygen propulsion. The safety risk remained unacceptable. Instead, post-war American torpedoes used improved conventional engines and eventually transitioned to electric and wire-guided systems that prioritized different capabilities. The Soviet Union, acquiring captured Japanese equipment through the occupation of Manchuria and Korean ports, pursued oxygen torpedo development more aggressively. Soviet torpedo designers studied Japanese manufacturing techniques and safety protocols, eventually fielding their own oxygen-powered torpedoes in the 1950s. These weapons armed Soviet submarines throughout the Cold War, though they never saw the combat that would test their effectiveness against the American warships they were designed to sink. The Type 93's legacy extends beyond its technical specifications. It represented a philosophy of naval warfare that prioritized offense over survivability, that accepted catastrophic risk in exchange for overwhelming capability, that committed national resources to perfecting a single weapon system for strategic effect. This philosophy produced victories when conditions favored its application, at Savo Island, at Tassafaronga, in the early surface actions around Guadalcanal. But it also produced defeats when opponents adapted. The Long Lance could not compensate for Japan's fundamental strategic weaknesses, inadequate industrial capacity, vulnerable sea lines of communication, a war economy unable to replace losses. American forces, though initially inferior in night combat capabilities, possessed the industrial base to absorb defeats, learn from them, and deploy countermeasures faster than Japan could adapt. Radar-directed gunfire, improved damage control, defensive maneuvering doctrines, and aggressive destroyer tactics all eroded the Type 93's advantages. By 1944, the weapon that had seemed nearly unstoppable in 1942 had become just another torpedo, dangerous if it connected, but increasingly unable to do so against properly equipped and trained opponents. The tactical lessons of the Type 93's career remain relevant. Weapons performance alone does not determine victory. The Long Lance was technically superior to every Allied torpedo throughout the war, yet Allied forces won the Pacific War decisively. Superior weapons provide advantages that skilled enemies can partially mitigate through tactics, training, and technology. Reliance on a single weapon system creates vulnerabilities when that system's operational environment changes. Japanese forces built their entire night combat doctrine around the Long Lance's capabilities. When radar negated the cover of darkness, Japanese destroyers and cruisers found themselves unable to close to torpedo range consistently. The doctrine that had worked brilliantly in 1942 became increasingly obsolete by 1944. No alternative approach had been developed because none had seemed necessary. The Type 93 also demonstrated the importance of intelligence and understanding enemy capabilities. Allied forces spent 2 years significantly underestimating Japanese torpedo performance. This failure cost hundreds of lives and multiple ships that might have survived with better tactical awareness. When American intelligence finally recognized the Long Lance's true capabilities, tactical doctrine changed rapidly. Engagement ranges increased. Evasive maneuvering became standard procedure when torpedo attack seemed possible. Radar operators were trained to track potential torpedo spreads by their source ship's movements. These adaptations reduced the Type 93's effectiveness substantially, not by matching its performance but by nullifying the tactical circumstances under which it was most dangerous. The men who designed, manufactured, and deployed the Type 93 understood they were creating a weapon at the edge of practical possibility. Rear Admiral Kishimoto, who led the initial development program, later stated that oxygen torpedo work required accepting risks that peacetime industrial safety standards would never allow. Engineers at Kure Arsenal knew their work was dangerous. They proceeded because their nation's strategic situation offered no alternative. The destroyer and cruiser crews who handled these weapons daily understood the consequences of mistakes. Oxygen leaks, improper maintenance, or damage to loaded torpedo tubes could destroy their ships faster than enemy action. They accepted these risks because the weapon gave them the ability to hurt ships much larger and more powerful than their own. This willingness to trade safety for capability produced a weapon that dominated the first phase of the Pacific War's surface actions. It also produced casualties that were never publicly acknowledged. Japanese destroyers occasionally suffered mysterious explosions in port or during handling evolutions. Official records attributed these to various causes, but many resulted from Type 93 accidents. The number of such incidents increased as the war continued and maintenance standards declined due to material shortages and exhausted crews. By 1945, some Japanese naval officers privately questioned whether the Longlance remained worth its operational cost. The question became moot. The weapon had been designed for a type of warfare, surface gun and torpedo action at night, that American radar had made nearly obsolete. In the final year of the war, Japanese surface forces rarely attempted the night torpedo actions that had been their primary offensive capability. American air power and submarine warfare had attrited the destroyer force to the point where coordinated night attacks became impossible. The ships that survived into 1945 spent most of their time tied up at dock or operating in waters so close to Japan that American air strikes found them easily. Their torpedoes, carefully maintained through years of war, remained loaded but unfired. When Japanese destroyers were finally sunk by American carrier aircraft or surface bombardment, their Type 93s often detonated as the ships went down, adding to the violence of their final moments. The technical specifications of the Type 93 reveal the engineering challenges that Japanese designers overcame through persistence and ingenuity. The torpedo's wet heater engine operated at pressures and temperatures that pushed material science to its limits. The combustion chamber had to withstand pure oxygen at 550 pounds per square inch while maintaining stable fuel-oxygen ratios across varying sea temperatures and depths. The gyroscope system required precision machining capabilities that Japan's heavy industries had only recently developed. Each gyroscope was hand-assembled by skilled technicians, calibrated individually, and tested through extended trial runs before installation. The production rate never exceeded 30 completed Type 93 torpedoes per month at Kure Arsenal, even at peak wartime production. This limited supply meant that destroyers and cruisers could not expend torpedoes freely in combat. Every Longlance fired represented hundreds of engineering hours and scarce materials. Japanese commanders understood this constraint. Torpedo expenditure was carefully tracked. After major surface actions, detailed reports documented how many torpedoes were fired, estimated hit percentages, and assessed whether the expenditure was justified by results. Following the Battle of Tassafaronga, where 44 torpedoes sank one cruiser and crippled 3 others, Japanese naval staff considered the exchange favorable despite the loss of Takanami. The ratio of for enemy heavy cruisers disabled for 44 torpedoes expended represented acceptable economics in Japan's attrition strategy. But after the Battle of Kolombangara in July 1943, where Japanese destroyers fired 64 torpedoes and achieved only 1 cruiser damaged, questions arose about whether the Longlance's effectiveness was declining as American forces learned to evade through aggressive maneuvering. The statistics supported this concern. In 1942, Japanese surface forces achieved an estimated 9% hit rate with Type 93 torpedoes, 9 hits for every 100 launched. By 1943, this had declined to approximately 4%. In 1944, the hit rate fell below 2%. Several factors contributed to this decline. American radar allowed earlier detection and more time for evasive maneuvers. American doctrine evolved to emphasize unpredictable zigzag patterns during night actions, making straight-running torpedoes less effective. American damage control improved dramatically, allowing ships to survive torpedo hits that would have been fatal earlier in the war. The cruiser USS Minneapolis, despite losing her entire bow to a Type 93 hit at Tassafaronga, was repaired and returned to service. This resilience frustrated Japanese planners who had assumed that torpedo hits would result in sinkings, not merely damage. The survivors, both men and ships, carried different lessons from the war. Japanese officers who had fought in the surface actions of 1942 and 1943 maintained that the Long Lance had been decisive in those engagements and that only America's industrial superiority prevented Japan from winning the attrition campaign the weapon was designed to enable. American officers who had faced Type 93 torpedoes at Savo Island, Tassafaronga, and other night actions emerged with respect for Japanese capabilities and a determination never to be surprised by an enemy weapon again. Post-war American naval doctrine emphasized continuous intelligence collection and technological surveillance. The Long Lance had taught a generation of American officers that assumptions about enemy capabilities can be fatal. When recovered Type 93 specimens were displayed at the Naval Academy in Annapolis and the Navy Department in Washington, they served as reminders of what happens when a Navy underestimates its opponent. These torpedoes, pulled from Pacific battlefields and shipped back to the United States for study, represented more than just captured equipment. They represented the cost of intelligence failure, the cruisers sunk, the sailors killed, the battles lost because American forces entered combat without understanding what they faced. The technical data extracted from captured Type 93s informed American torpedo development for decades. Engineering studies examined the oxygen handling systems, the warhead design, the propulsion mechanics. Some elements were incorporated into American weapons. Others were noted as interesting but impractical given different industrial capabilities and safety requirements. The most significant lesson involved weapon philosophy rather than specific technology. Japanese designers had prioritized maximum performance and accepted the costs. American designers traditionally prioritized safety and reliability, accepting somewhat reduced performance. The Long Lance demonstrated that in combat, the higher-performing weapon wins engagements even if it is less safe to operate. This realization influenced post-war weapons development across multiple domains. Aircraft, missiles, electronic systems, and submarines all saw performance goals adjusted upward despite increased operational risk. The numbers tell the story most clearly. 22 Allied warships sunk solely or primarily by Type 93 hits, 8 cruisers, 13 destroyers, 1 fleet aircraft carrier. An additional 12 warships crippled severely enough to require months of repairs. Thousands of sailors killed in explosions so violent that survivors described ships simply disintegrating. Against these Allied losses stand the Japanese casualties, approximately 40 cruisers and destroyers lost when their Type 93 torpedo loads detonated after bomb or shell hits, plus uncounted handling accidents and operational mishaps. The weapon killed effectively but also killed indiscriminately. In raw exchange ratios, the Type 93 more than paid for itself. Japanese destroyers armed with Long Lances sank or crippled more Allied tonnage than they themselves displaced. This is the metric by which naval weapons are ultimately judged, their ability to generate favorable exchange ratios under combat conditions. By this measure, the Type 93 was the most successful torpedo of World War II. Yet this success came at strategic cost. Resources devoted to oxygen torpedo development and production might have been allocated to radar systems, electronic warfare capabilities, or improved damage control technology, areas where Japan lagged significantly behind Allied forces. The choice to perfect one weapon system at the expense of broader technological advancement reflected Japanese naval culture's emphasis on offensive spirit and individual weapon quality. This philosophy produced tactical victories and strategic defeat. American forces, with their emphasis on systematic technological improvement across all domains, eventually overwhelmed Japanese capabilities not through superior individual weapons but through superior integrated systems. The Long Lance could sink cruisers at unprecedented ranges, but it could not prevent American submarines from strangling Japan's merchant fleet. It could devastate surface forces in night actions, but it could not stop American carrier aircraft from achieving air superiority over the Pacific. It was a superb weapon deployed by a navy that ultimately lost the war despite possessing tactical advantages in multiple areas. The question of what might have been haunts the Long Lance's history. If Japan had possessed adequate radar to match the Type 93's capabilities, would night surface actions have continued to favor Japanese forces throughout the war? If American forces had captured intact Type 93 specimens in 1942 instead of 1943, would tactical adaptations have occurred sooner and reduced Allied losses? If Japanese industrial capacity had allowed production of sufficient oxygen torpedoes to arm every destroyer and cruiser with full loads throughout the war, would the attrition strategy have succeeded in its objective of weakening the American fleet before the decisive battle? These counterfactuals cannot be answered definitively, but they illuminate the constraints under which both sides operated. Japan developed superior torpedo technology but lacked the industrial depth to exploit it fully. America entered the war with inferior torpedo technology but possessed the resources to absorb defeats while developing countermeasures. The Long Lancer's story is ultimately about how technological superiority in one domain cannot compensate for systemic weaknesses in others. Japanese forces won battles with the Type 93 but lost the campaign because battles are decided by weapons while campaigns are decided by resources, logistics, and industrial capacity. The individual engagement might favor the side with better torpedoes, but the extended war favors the side with more ships, more fuel, more trained crews, and more replacement capacity. By 1944, the Imperial Japanese Navy faced catastrophic shortages in all these areas. American submarines had sunk more than half of Japan's merchant fleet, strangling the flow of oil from the Dutch East Indies and raw materials from Southeast Asia. Training programs could not replace experienced destroyer captains and torpedo specialists killed in earlier actions. Shipyards prioritized damage repairs over new construction because American air strikes had disrupted production schedules. The oxygen generation equipment required for Type 93 operations depended on electrical power and industrial chemicals that were increasingly unavailable as American bombing intensified. Some destroyers entered combat with empty torpedo tubes because their oxygen generation systems had failed and no replacement parts existed. Others carried torpedoes loaded months earlier. Their oxygen tanks leaking slowly, their reliability questionable. The weapon that had terrified American cruiser captains in 1942 became a symbol of Japan's declining naval power by 1945. The human cost of the Type 93's development and deployment remains difficult to quantify precisely. Japanese naval records indicate that more than 400 engineers, technicians, and sailors died in accidents related to oxygen torpedo handling, production, and testing between 1928 and 1945. This figure almost certainly underestimates actual casualties because many incidents were classified or attributed to other causes for security reasons. American and Allied casualties directly attributable to Type 93 hits exceeded 6,000 dead and wounded. The ships sunk by Long Lance torpedoes carried approximately 5,800 officers and enlisted men at the time they were hit. Survival rates vary dramatically depending on circumstances. When the destroyer Cortana was struck at the Battle of the Java Sea, fewer than 50 men survived from a crew of more than 150. The cruiser Quincy, sunk at Savo Island, lost approximately 370 of her 600-man crew. But the cruiser Minneapolis, though catastrophically damaged at Tassafaronga, lost only 37 men because her crew's damage control efforts contained the flooding and prevented the ship from sinking. These human costs shaped how both navies approached weapons development in the post-war era. Japanese self-defense force maritime doctrine, when Japan rebuilt its navy in the 1950s, emphasized defensive systems and anti-submarine warfare rather than offensive torpedo capabilities. The memory of ships destroyed by their own weapons when Type 93 loads detonated under attack influenced this defensive orientation. American naval doctrine incorporated the lesson that technological surprise can be decisive and deadly. Post-war intelligence programs prioritized understanding enemy weapons capabilities before combat exposed American forces to unknown threats. The Office of Naval Intelligence established permanent sections dedicated to tracking foreign torpedo development, a direct result of the Long Lance experience. When Soviet submarines began deploying oxygen-powered torpedoes in the 1950s, American anti-submarine forces understood the threat immediately and developed countermeasures rather than being caught unprepared as they had been in 1942. The broader strategic context of the Type 93's deployment reveals how weapons technology intersects with national military doctrine in complex ways. Japan's decision to invest heavily in torpedo development reflected a strategic assessment that proved both correct and tragically limited. Correct in identifying torpedoes as weapons that could allow inferior numbers to defeat superior forces in individual engagements. Limited in failing to account for how superior opponents would adapt once the initial surprise faded. This pattern, achieving tactical success through superior weapons while losing strategic campaigns through inadequate resources, repeated throughout the Pacific War in multiple domains. Japanese naval aviation at the war's start possessed better carrier aircraft and more experienced pilots than American forces. Japanese submarines deployed better torpedoes than their American counterparts and operated with greater initial success. Japanese naval artillery, particularly on battleships and heavy cruisers, demonstrated superior accuracy in early engagements. Yet all these tactical advantages eroded under the pressure of industrial attrition. American forces replaced losses faster than Japanese forces could inflict them. American technology improved more rapidly than Japanese technology because American industrial capacity allowed parallel development of multiple systems simultaneously while Japanese industry had to prioritize ruthlessly. The Long Lance program consumed resources that might have developed radar systems competitive with American technology. The choice between perfecting oxygen torpedoes and deploying adequate radar created a technological fork in the road. Japan chose torpedoes and paid the price in night battles where American radar detected Japanese forces before they could reach favorable engagement ranges. The engineering legacy of the Type 93 extends into modern naval warfare in ways that would surprise its original designers. Contemporary supercavitating torpedoes, which create gas bubbles around their bodies to reduce water resistance and achieve speeds exceeding 200 knots, face similar challenges to those Kishimoto and Asakuma solved in the 1920s and 1930s. Managing the interaction between high-pressure gases and high-speed underwater propulsion requires the same careful attention to materials science, fluid dynamics, and safety protocols that the Long Lance program developed. Modern Russian Shkval torpedoes, descendants of Soviet oxygen torpedo programs that drew directly from captured Japanese technology, demonstrate that the fundamental concepts pioneered for the Type 93 remain viable in the missile age. Wire-guided torpedoes, which allow submarines to steer their weapons after launch, represent a different solution to the problem the Long Lance addressed through sheer range and speed. Instead of firing from extreme distances and hoping the target maintains a predictable course, modern torpedoes are launched from closer ranges but can be directed toward evasive targets. This approach prioritizes accuracy over range, a different philosophical choice than the one Japanese designers made. Yet both approaches seek the same objective, allowing smaller platforms to destroy larger, more heavily armed opponents through weapons that can bridge the distance between unequal forces. The Type 93 represented one answer to this eternal naval problem. Its success in 1942 and limitations by 1944 demonstrate that no weapons technology maintains permanent superiority. Every advantage provokes countermeasures, every innovation triggers counter-innovation, and every period of dominance contains the seeds of obsolescence. The tactical doctrine built around the Type 93 demonstrated both the strengths and limitations of weapon-centric military planning. Japanese destroyer divisions trained extensively for coordinated torpedo attacks, practicing until crews could execute complex maneuvers in complete darkness by following signal lights and timing. These exercises emphasized launching large torpedo spreads from multiple ships simultaneously, creating fields of intersecting torpedo tracks that would overwhelm target evasion capabilities. The theory was sound. If 8 destroyers each launched 8 torpedoes in a coordinated attack, 64 weapons would converge on the target area from different angles over a period of several minutes. Even aggressive maneuvering could not evade such saturation. This doctrine worked brilliantly at Tassafaronga, where Tanaka's 8 destroyers overwhelmed American cruiser defenses through coordinated launches. But the doctrine required prerequisites that became increasingly difficult to satisfy as the war progressed. First, it required intact destroyer divisions of 6 to 8 ships operating together. American attrition reduced Japanese destroyer strength from 180 ships in December 1941 to fewer than 40 by August 1945. Finding enough operational destroyers to form effective attack groups became impossible. Second, the doctrine required sea room to execute coordinated maneuvers. In the confined waters around the Solomon Islands, destroyers could mass for attacks. In the Philippines and later around Japan itself, American air power forced Japanese destroyers to operate in small groups or individually, precluding coordinated tactics. Third, the doctrine required darkness to prevent American air strikes and reduce gun accuracy. By 1944, American night fighters operated routinely, and illumination rounds could turn night into day at critical moments. The conditions under which Long-Lance doctrine achieved maximum effectiveness existed primarily in 1942 and early 1943, and never returned. The photographs of Type 93 torpedoes displayed in museums across the United States, Japan, and other nations show weapons that appear almost crude by modern standards. The 29-foot steel tubes lack the sleek lines of contemporary weapons. The gyroscope mechanisms, visible in cutaway exhibits, seem mechanical and vulnerable compared to modern electronic guidance systems. The oxygen tank, when pointed out to visitors, usually provokes surprise that anyone would build a weapon around such a volatile substance. Yet these museum pieces represent sophisticated engineering that pushed the boundaries of what was possible with 1930s technology. The metallurgical research required to create oxygen-resistant alloys for the pressure tanks advanced Japanese material science in ways that benefited other weapons programs. The precision manufacturing techniques developed for gyroscope production improved quality control standards across Japanese heavy industries. The safety protocols created for oxygen handling provided templates for working with other hazardous materials in military applications. The Long-Lance program, though focused on a single weapon system, generated technological spillover effects that influenced Japanese engineering more broadly. This is often the case with advanced weapons development. The specific weapon may become obsolete, but the industrial and scientific capabilities developed in its creation persist and find applications elsewhere. The personal accounts of sailors who served aboard ships equipped with Type 93 torpedoes provide insight into the psychological dimension of operating such weapons. Japanese destroyer crews knew they sailed aboard ships carrying tons of compressed oxygen and high explosive, volatile combinations that could destroy their vessels instantly if hit in the wrong place. This knowledge shaped crew behavior and shipboard culture. Torpedo handling evolutions were conducted with ritual precision. Officers supervised every step of the loading process. Before any torpedo movement, announcements cleared non-essential personnel from the area. Fire parties stood ready with specialized equipment designed for oxygen-fed fires. Conventional water-based firefighting could spread burning oxygen throughout the ship. The tension during combat was amplified by awareness that enemy shells striking torpedo storage areas could trigger catastrophic secondary explosions. Crews serving aboard American ships faced similar risks from their own ammunition magazines, but conventional explosives were less sensitive to shock than Shimose-loaded torpedoes with oxygen propulsion. Japanese sailors developed fatalistic attitudes toward these dangers. The warrior code of Bushido emphasized acceptance of death in service to the emperor, and this cultural framework helped crews cope with operating weapon systems that could kill them as easily as they killed enemies. Western observers often misinterpreted this fatalism as recklessness or disregard for safety. In reality, Japanese procedures for oxygen handling were more rigorous than American procedures for conventional torpedoes. The difference was that Japanese commanders accepted risks that Western militaries rejected outright, believing that superior weapons justified elevated danger to their own forces. This calculation proved correct in tactical terms. The Long-Lance's effectiveness exceeded the losses it caused to Japanese ships. But the psychological cost of operating such weapons eroded crew morale as the war continued and losses mounted. Sailors who survived multiple ships sinking from Type 93 detonations after enemy hits developed understandable reluctance to serve on ships carrying the weapons. By 1945, some destroyer crews reportedly became less meticulous about loading procedures and safety protocols, a dangerous decline in standards that contributed to additional accidents. The logistical infrastructure supporting Type 93 operations reveals another dimension of the weapon's complexity. Each warship carrying Long-Lances required specialized equipment and trained personnel. The oxygen generation system occupied significant space below decks and required constant maintenance. Electrolysis units separated oxygen from seawater, compressors pressurized the gas to 550 pounds per square inch, and storage tanks held the compressed oxygen until needed for torpedo loading. This equipment consumed electrical power continuously even when the ship was not in combat. The process of filling a single Type 93's oxygen tank required approximately 4 hours, meaning that a destroyer with 16 torpedoes needed 64 hours of continuous oxygen generation to prepare a full loadout. Ships could not rapidly replenish expended torpedoes at forward bases unless those bases had their own oxygen generation facilities. Establishing such facilities required transporting specialized equipment to advanced locations and defending them against air attack. By 1943, American air strikes had destroyed most forward oxygen generation sites, forcing Japanese destroyers to return to major fleet bases for rearming. This extended the logistics cycle and reduced the tempo of operations Japanese forces could sustain. Additionally, the torpedoes themselves required careful handling during loading. Each Type 93 weighed nearly 3 tons and had to be lifted from below-deck magazines, positioned on deck, and loaded into tubes using specialized equipment. The process could not be rushed. A drop torpedo could detonate or rupture its oxygen tank, creating a catastrophic shipboard fire. Crews trained extensively in loading procedures, but under combat conditions or when working with damaged equipment, accidents occurred. Several Japanese destroyers were lost or damaged by torpedo handling accidents during replenishment operations, though exact numbers remain uncertain because such incidents were often attributed to enemy action in official records. The comparative analysis of Japanese and American torpedo technology reveals how different industrial philosophies shaped weapons development. American torpedo designers in the 1930s prioritized reliability and safety because American doctrine anticipated lengthy overseas deployments where weapons would spend months aboard ship before use. Torpedoes had to function reliably after extended storage in tropical heat and saltwater environments. This requirement drove design choices toward robust, simple mechanisms that could tolerate rough handling and variable maintenance standards. The Mark 15 destroyer torpedo embodied this philosophy. Its compressed air and alcohol propulsion system was conventional and well understood. Its 827-pound warhead used stable TNT explosive that required direct detonation to explode. Its gyroscope was simple and rugged. The weapon worked reliably under field conditions, though its performance parameters were unexceptional. Japanese designers made different choices. They prioritized maximum performance and accepted reduced reliability and safety margins. Type 93 torpedoes required careful handling, precise maintenance, and trained specialists for loading and firing. They could not tolerate rough handling or casual maintenance. But when properly employed, they outperformed every comparable weapon. This reflected fundamental differences in how the two navies approached warfare. The American approach emphasized system integration, ensuring that weapons, sensors, communications, and tactics worked together effectively. No single element needed to be superior as long as the combined system produced favorable outcomes. Japanese doctrine emphasized excellence in individual weapon systems. If torpedoes were superior, torpedo attacks would succeed regardless of other factors. If aircraft were superior, air attacks would prevail. This approach worked when Japanese forces could dictate engagement terms and exploit their advantages in isolation. It failed when American forces used integrated systems to neutralize specific Japanese advantages. American radar detected Japanese torpedo approaches early enough to maneuver clear. American damage control saved ships that Japanese planners assumed would sink from single torpedo hits. American air cover prevented Japanese destroyers from reaching favorable attack positions. The Long Lance remained superior to American torpedoes throughout the war, but this superiority mattered less and less as American systems evolved to counter it. The philosophical lesson extends beyond World War II. Military forces face constant choices between perfecting individual capabilities and integrating adequate capabilities into effective systems. The optimal choice depends on strategic circumstances. Japan in 1941 could not match American industrial capacity or technology across all domains, so focusing on selected areas where superiority was achievable made strategic sense. The error was failing to recognize that opponents with greater resources would eventually develop countermeasures that negated specific advantages. A sustainable strategy requires either maintaining continuous technological superiority, difficult for resource-limited nations, or accepting that technological parity may be sufficient if integrated effectively into combined arms doctrine. The final months of the Type 93's operational life saw the weapon employed in increasingly desperate circumstances. By early 1945, the Imperial Japanese Navy had been reduced to a shadow force. Most battleships and carriers had been sunk. Cruisers were tied up in port for lack of fuel. The destroyer force, once numbering nearly 200 ships, had been whittled down to fewer than 50 operational vessels. Those that remained faced impossible missions, suicide attacks on American invasion fleets, one-way transport runs to isolated garrisons, and hopeless attempts to defend Japanese home waters against overwhelming American naval power. The long-lance torpedoes aboard these destroyers represented weapons designed for a type of warfare that no longer existed. The night surface engagements that had been Japanese specialty in 1942 and 1943 were no longer tactically possible. American forces possessed complete air superiority and could detect Japanese ships moving toward attack positions hours before they arrived. Japanese destroyers attempting to approach American invasion fleets were intercepted by radar-equipped destroyers screening the transport areas or destroyed by carrier aircraft before reaching torpedo range. In the few surface actions that occurred during this period, Japanese destroyers launched their Type 93s more in defiance than tactical calculation, knowing the weapons had minimal chance of hitting evasive targets under heavy fire. The Battle of Ormuz Bay in December 1944 exemplified this futility. Japanese destroyers attempting to land reinforcements on Leyte were attacked by American destroyers and aircraft. The Japanese ships launched torpedoes at maneuvering American destroyers that detected the launches via radar and turned away at high speed. None of the Type 93s hit. The Japanese destroyers were subsequently sunk by gunfire and air attack. Their crews died without inflicting significant damage on enemy forces. These final engagements demonstrated that superior weapons cannot overcome impossible tactical situations. The long-lance remained the best torpedo of the war even in 1945, but in the strategic environment that existed by then, being the best torpedo mattered little. The cultural memory of the Type 93 in Japan and the United States reflects each nation's broader narrative about the Pacific War. In Japan, the long-lance is remembered as a weapon that worked as designed, a symbol of Japanese engineering excellence and tactical skill that nearly offset American material superiority. Popular histories and technical publications emphasize the torpedo's specifications and early victories while treating later defeats as consequences of overwhelming enemy numbers rather than fundamental weapon limitations. This narrative serves a cultural need to find pride in technological achievement even within the context of catastrophic national defeat. The long-lance represents something Japan did better than anyone else, a point of light in the darkness of 1945. In American memory, the long-lance occupies a different role. It represents the danger of underestimating enemies and the cost of intelligence failures. The defeats at Savo Island and Tassafaronga remain embarrassing chapters in U.S. Navy history, studied in war colleges as examples of how tactical surprise and superior weapons can overcome numerical superiority. The eventual American victory over Japanese forces despite the long-lance advantage reinforces narratives about American adaptability and industrial power. These differing memories shape how each nation approaches current military challenges. Japanese defense planners, inheriting the legacy of engineering excellence overmatched by enemy resources, emphasize quality over quantity in weapons procurement. American planners, remembering how industrial capacity allowed recovery from early defeats, maintain faith in the ability to outproduce and out-innovate opponents. Neither memory is entirely accurate, but both influence decision-making decades after the last Type 93 was fired in combat. American rocket programs in the 1940s and 1950s drew on German VR-2 technology not because American engineers copied German designs directly but because studying German solutions to propulsion and guidance problems illuminated paths that American research could follow. The preservation of Type 93 specimens in museums worldwide serves purposes beyond historical education. These artifacts represent physical evidence of engineering achievement under extreme constraints. Modern students of naval engineering study the oxygen handling systems to understand how 1930s technology addressed problems that remain challenging with contemporary materials and methods. The precision machining visible in museum examples, particularly in gyroscope components and valve assemblies, demonstrates manufacturing capabilities that required years to develop. Japan's heavy industries in the 1920s lagged significantly behind Western counterparts in precision metalworking. The Type 93 program forced rapid advancement in this area because the weapon's performance demanded tolerances that Japanese factories had never achieved. Engineers had to develop new machine tools, train specialized machinists, and establish quality control procedures that matched or exceeded Western standards. This industrial evolution benefited Japanese manufacturing broadly. The skills and equipment developed for torpedo production transferred to other weapons systems and eventually to post-war civilian industries. Japan's post-war emergence as a manufacturing powerhouse in precision products, cameras, watches, electronics, built partially on industrial capabilities developed during wartime weapons programs like the Long Lance. This historical connection is rarely acknowledged in corporate histories or industrial narratives, but the technological lineage exists. The machinists who produced gyroscope components for Type 93 torpedoes in the 1930s trained the next generation who worked in post-war electronics factories. The quality control philosophies developed to ensure torpedo reliability influenced the manufacturing excellence for which Japanese industry became famous. War and its weapons left unexpected legacies in the peace that followed. Similarly, Soviet torpedo programs benefited from studying Japanese oxygen torpedo technology not by copying the Long Lance exactly but by understanding the engineering challenges Japan had solved and applying similar solutions to different design problems. The post-war Soviet Navy, recognizing that NATO naval forces would possess numerical and technological superiority in most domains, invested heavily in torpedo technology as an asymmetric capability. Large, fast, long-range torpedoes fired from submarines could threaten American aircraft carriers despite the enormous disparity in overall fleet strength. This Soviet strategy paralleled Japanese thinking in the 1930s, used superior weapons in selected domains to offset general inferiority. The Shkval supercavitating torpedo, entering Soviet service in the 1970s, represented the conceptual descendant of the Long Lance. It could not match the Type 93's range, but it achieved speeds exceeding 200 knots by creating a gas bubble that dramatically reduced water friction. Like the Long Lance, the Shkval was dangerous to its users as well as targets. The supercavitation system was temperamental and the weapon could not turn after launch, requiring precise initial targeting. Like the Long Lance, the Shkval represented a weapons philosophy that prioritized maximum performance over safety and reliability. Soviet torpedo crews learned many of the same lessons Japanese crews had learned decades earlier about operating weapons that demanded respect and meticulous handling. The connection between the Type 93 and modern torpedoes extends beyond hardware. The tactical doctrines developed for Long Lance employment influenced submarine warfare thinking throughout the Cold War. The emphasis on pre-launch positioning to achieve optimal firing geometry, the use of spread launches to increase hit probability against maneuvering targets, and the calculation of target course and speed to compensate for long torpedo run times, all these tactical principles that Japanese destroyer crews mastered in the 1930s and 1940s became foundational concepts in submarine torpedo tactics. American submarine officers studying torpedo doctrine at the submarine school in New London learned these principles by analyzing Japanese torpedo attacks from World War II. The mathematical relationship between target course, speed, torpedo speed, and firing solution remained constant regardless of specific weapons employed. Understanding how Japanese destroyers achieved successful torpedo attacks despite the limitations of straight-running weapons provided insights applicable to more sophisticated systems. In this sense, the Long Lance continued teaching lessons decades after the last one was fired. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world.